As we get ready to start a review of TCP versus UDP and the three-way handshake and that kind of thing, quite a few of you are thinking, wait a minute, did I wander into the wrong class here? This is the CCNP route class, right? Yes, it is. The CCNA class is down the hall. But when they refreshed the CCNP, they did move some of the TCP UDP material back into the CCNP world. So I know the temptation, especially for those of you who just recently got your CCNA, is to say, well, I know all this stuff. I don't really need to go over it. Please don't take that approach, especially if it has been a while since you got your CCNA, because a lot of this material, we don't really use it every single day. It works so well, we don't give it a lot of thought. So for a certification exam, of course, we want to be super sharp on it, which is why you should spend a little time with these review videos at the beginning of the course. Also, I have thrown in a few new features here for you as far as TCP goes, so it is not just a repeat of what you did in your CCNA course. Now, if this is the first section of videos you've watched in my CCNP route course, I want to tell you point blank, there aren't a lot of labs in this particular section. As a matter of fact, there are hardly any, because this theory really doesn't lend itself to work on the live routers. There's plenty of that coming, believe me. Plenty of advanced EIGRP, OSPF, BGP videos, all kinds of stuff. This is really the only section that's light on labs. Having said all that, let's jump right in. We know they run at the transport layer of the OSI model. They also perform something called multiplexing, but frankly, that's about it for the similarities when it comes to TCP and UDP. TCP absolutely guarantees our segment delivery. We'll take all the guarantees in the networking we can get. It performs error detection, we like the sound of that, and it performs windowing. TCP is connection oriented, and that means that we have that two-way communication between the endpoints taking place before the data segments actually start going out. Now, UDP performs best effort delivery. That sounds good, but let's face it, when somebody comes to you and says, hey, I did my best, that usually means they didn't get the job done, right? Well, UDP gets the job done, but it's just not guaranteed to get done. There's no error detection mechanism because it doesn't have the sequence and ACK numbers that TCP does in order to perform that error detection. UDP doesn't offer windowing, and it's also connectionless. There's no pregame communication, so to speak, between the endpoints. The captains don't go to midfield and shake hands. The data exchange just starts. Now, even if you don't even remember what windowing is, and I'm sure you do, but if you don't, we're going to review it in a moment, you have to admit that TCP sounds a lot better than UDP, because I'll take a guarantee of delivery over best ever delivery any day of the week. But as a future CCNP, you know that's not the case as far as using TCP for everything and UDP for nothing. Traffic doesn't get any more delay sensitive than voice and video traffic. If you get just a little bit of jitter in a voice over IP call or any of your Cisco voice, oh man, your phone starts ringing like crazy. So we can't really afford any delays. Well, all of your voice and video traffic, it's using UDP. Well, let's think about why when we take a look at a curious little TCP process, that three-way handshake. Well, I used to do, when I would do this in an in-person course in CCNA class, I would ask someone to do a three-way handshake with their neighbor, and I just always got funny looks. Because obviously it's hard for humans to do, but it's easy for TCP, because before TCP can even send data segments, the involved devices have to agree on some parameters in advance. And that includes what we call the ISN, the initial sequence number. Now these parameters are agreed upon during the handshake, and this handshake starts with the initiator sending a TCP segment with the synchronization bit set, usually just called the SYN bit, because that sounds a lot more fun. The primary value synced here is that TCP sequence number. And what happens is the recipient of this responds with a TCP segment of its own, and that one has the acknowledgement bit set. See what I did there? ACK. In addition to the SYN bit. So at this point, with step 2 of the three-way handshake, we have a TCP segment going back with the SYN and the ACK bit set, which is usually just referred to as a SYN-ACK. Now, part of that SYN-ACK is the server acknowledging receipt of the original SYN. So it makes sense for the server receiving the SYN-ACK to ACK it in return, and that is the final shake, if you will, of our three-way handshake. And now I have for you, coming up on the board, an exclusive illustration of the UDP three-way handshake. And there it is, absolutely nothing, because UDP doesn't have a three-way handshake. that client's just going to start throwing stuff at that server. It sounds like another strike against UDP to me. We'll see how that works out. But let's talk about flow control and windowing. One of the values negotiated during the three-way handshake is the initial size of the window. And what's interesting here is that the recipient of the data is the one saying, hey, I am going to dictate how fast we're going here. And the size of the window determines how many bytes of data the recipient is willing to take in before it has to send an ACK back. And this window is dynamic because as the recipient says, okay, I can handle the window size that's coming in right now. I can handle the data with no problem. I'm not dropping anything. The recipient tells the sender, step on the gas a little bit. Let's go a little faster. Well, this dynamic behavior gives this feature the name the TCP sliding window. And, the recipient says, okay, let's go up to 5,000 bytes. And of course the sender's like, okay, let's do that. Well, as the recipient gets a little overwhelmed by the amount of incoming data, maybe it starts dropping a few segments here and there, it tells the recipient, okay, let's hit the brakes a little bit. Let's ease off the gas. Slow that flow down and shrink the size of the window. And the flow control, this flow control allows segment transmission to stay close to the maximum input of the recipient while allowing the recipient to say, hey, wait a minute, at some point we got to slow this thing down a little bit. Now, I want to talk to you about an option that sounds familiar. It's called the TCP window scale option. And this allows us to go way beyond the TCP receive window max of 65,535 bytes. Now, this feature should be used with care and only in certain situations because some firewalls and routers cannot run it properly. Now, the one thing also in this section that I want to mention is that I do give you a couple of Wikipedia and Cisco links to check out. They're not required reading for the exam. I don't do that very often, but with some of these topics, we're just touching on them, and you might want to say, hey, I want to know more than this. And I sound like the guy, on CBS for, if you'd like to learn more, visit your local library. Well, here I'm saying, visit Wikipedia or Cisco. I don't do that very often, but I do it a couple times here in this section. Again, I've got a link here for you from Wikipedia, the TCP window scale option. Not required reading, certainly, but it's highly recommended. Now, to enable TCP window scale on a Cisco router, we're going to use IP TCP window size. And I'm just going to show this to you on the whiteboard. And it's interesting that just about every iOS I've seen, you'll notice it just says here IP TCP window size, and that's it. There's nothing else. So you need to know that that is bytes. And of course, one very important feature here, one thing about this feature, it must be enabled on both hosts involved in the TCP session, otherwise it really wouldn't do us much good. Now let's step back to flow control for just a moment. UDP has no form of flow control. Yep, that's it, right? Another strike against UDP. But actually TCP having flow control and UDP not having it can actually work against TCP when that congestion occurs. Well, let's say that you have UDP and TCP flows going across your network, point A to point B, and some congestion is detected. How does each protocol react according to what we've seen so far? Well, TCP uses its flow control, and the recipient says, hey man, you got to throttle back a little bit. You got to slow down. UDP doesn't do spit. It just keeps on sending. Well, what happens is, as TCP starts surrendering some of that bandwidth, UDP grabs it. UDP says, hey, I don't know where this extra bandwidth came from all of a sudden, but I'm taking it. Well, it's pretty rude on UDP's part, but whether you call this TCP starvation or UDP dominance, I've seen it called both, so be familiar with both terms, it's not a good situation. And occasionally when I'm teaching a course where traffic classes are taught, people say, well, I really need to put all this traffic in different classes. And if you're not familiar with that term, it just means that we're saying, okay, we're putting this traffic in this high priority queue and some other traffic we're giving it lesser priority and other traffic very low priority. And what happens there, of course, is you will tend to put your delay sensitive traffic in the high queues, but you also should perhaps separate your TCP and UDP traffic. Because when your TCP and UDP traffic is in the same class, we're not we're not breaking the flows up in any way, well, that's where the starvation and dominance comes in. Mixing UDP and TCP traffic without using some form of quality of service, it's just not the best idea. Sometimes you just can't help it, but you could end up with lower throughput for your TCP traffic while still running into latency because UDP just takes that extra bandwidth that TCP is freeing up and takes it for itself. One more issue with TCP's flow control, unbelievably, and that is global synchronization. And if you have a lot of hosts with active TCP sessions and the recipient is overloaded, what happens is flow control kicks in, and again, I know you've heard it a couple times by now, but the hosts are going to be told you got to slow down. The problem is they all slow down at the same time, so as congestion eases, flow control indicates to the hosts, hey, wait a second, now we need to go faster. Well, then all your hosts start doing that at the same time. So what you end up with, instead of a nice even rate of traffic transmission, you have peaks and you have valleys. What you'll have is a few seconds where your line is way underutilized, your bandwidth is underutilized, and then a couple seconds later it's just being hammered. There's no in between with global synchronization. One form of taking care of that, weighted random early detection. That's one tool against global synchronization. Unfortunately, we can't get into the configuration of WRED here, but that is one good way to fight global synchronization. So we're sitting here looking at UDP and TCP, and it's like, why in the world do we even keep UDP around? Well, let's look at the headers for TCP and UDP. And there's our friend TCP right there at the top, and we got a source port and a destination port, sequence number and an ACK number, a lot of other values there that you see that UDP frankly just doesn't have. UDP's got source port, destination port, length, checksum, and data. That's it. Well, this difference in size gives us a hint to UDP's advantage over TCP, and that is that UDP has much less overhead. Excuse me. Because I do tell people, especially again going back to the CCNA course, you know, these are all great features you're learning about, but don't necessarily go back to your real-world network and implement all of them at one time. Because what do I always say? Everything you do on a router or a switch has a cost. Not a financial cost as much as a hit to the router resources. Now, TCP offers us many more features than UDP, a couple that we've got coming up in the next few videos, but the network features always come at a cost. And with TCP, that cost comes in the form of delays because we get additional overhead. And with the amount of voice and video traffic on today's networks, that is overhead we absolutely cannot afford. And that's the big reason why UDP is used for voice and video traffic, is the lower overhead. We will continue the case of UDP versus TCP with a similarity and a look at some TCP features that you didn't see during your CCNA training. And that's coming up next.